Okay. Yeah, someone. Okay. Okay, so shall we start? I think we can make a start. Okay. Sugar, maybe you want to close the door. Okay, so let's make a start. I think if you can switch off your, you mute yourself.
The microphone.
Yeah.
The microphone.
Okay, yeah, because my voice is echoing. I think it is still echoing.
Oh, it's the sound
From. Oh, okay. Okay. Anyway, so good afternoon, everyone, and welcome to our session today. Welcome to all of you who attended in person, especially in this snowy weather, and welcome to audience who joined us via Zoom online. So my name is Faize Arab Hassani. I am a lecturer in microelectronics, as some of you know me. So I am also the counselor of the IEEE student branch, and I will be chairing this session today. Just a few housekeeping points, especially for those people online. Try to keep your videos off and keep yourself muted. So we are recording the session, so hopefully you can rewatch the video later if you are interested. Then for people online, you can post your questions in the chat box at the bottom of the page, and we will get back to your question at the end of the session along with the questions that we receive in the room. So it is my great pleasure today to welcome our two speakers from EnSilica company. I'm sure that they will walk us through the operation at EnSilica and their Bristol office. Our first speaker is Mr. Davide Sarta. Davide is Vice President of System on Chip Engineering at EnSilica Bristol office. Davide graduated in Electronic Engineering at the University of Catania, Italy, with a master in control systems and a second master in low power silicon design, obtained at the Politecnico di Milano. He has over 25 years of experience in the development of complex digital SoC, with many products taped out successfully in mass production on process nodes down to 7 nanometer, and different applications ranging from 5G, AI, set-top boxes, cable gateway, and HPC. He's based in Bristol and currently manages the EnSilica SoC engineering organization based in Bristol, Oxford, Porto Alegre, and Bangalore. Our next speaker who will talk about the second part of the industry talk today is Mr. Leonardo Napolitano. Leonardo is Senior Principal DFT Engineer and EnSilica Bristol office. Leonardo graduated in Electronic Engineering at the University of Naples, Italy, with a Master in Industrial Robotics. With over 20 years of experience, he has been responsible for DFT implementation on many devices, from large to very large size, and using the most advanced DFT techniques used today on digital chips down to 7 nanometer process, and for applications ranging set-top boxes, hard disk drives, AI, 5G. Leonardo is also based in Bristol and currently leads the EnSilica DFT activities. Without further ado, let's welcome our speakers and enjoy this talk.
Great, thank you, Faiza. That's appreciated. I hope everybody can hear my voice and see me. Thanks for joining despite the weather today. Probably one of the worst in this year and last year, but I'm happy to see you here. Thanks for the introduction. I won't spend any more time to introduce myself. I think you did a good job there in saying a little bit of my background. So hopefully you can see the screen, and we can move to the next slide. So there is a lot to talk, so I'll probably go quick in some of the slides and focus a bit more on the technical topics which will be coming soon after the first interaction. I think it would be useful to present a little bit about EnSilica, just to explain where we come from, who we are, what we do. And then we'll dive immediately into the main silicon design functions. The topic, as you know, is about DFT, but it's important to, let's say, insert a DFT subject within the overall silicon design flow. So I will go for a description of what it is and then where DFT blends into the overall scheme. And then we'll dive more into exactly the DFT, and Leo will explain what it is. Of course, there is no way we can explain the details of DFT or create a DFT engineer in 1.5 hours talk. That will take probably like years to become an expert in DFT. But as we have discussed, the silicon design is quite a large subject in general. And the microelectronics, as you know, is also quite wide and deep. And the DFT it used to be a small subject up to 20 years ago. The situation has changed quite a lot, and we thought it was a good idea to bring that awareness to you guys, to the students, to the university. Also because, as I will explain better at the end of the presentation, there is a significant shortage of DFT engineer in the job market, and there is clearly a gap to fill here, and everything starts in the end at the university. So we thought, let's try to fill that gap going into the university and try to bring awareness of DFT, explain the challenges, and somehow the beauty also in those challenges that we are facing more and more every day with the increasing complexity of the silicon chips. There will be some real project example as well, which I will show. And then the last bit is about a career in silicon design in general and DFT in particular. So this is non-technical, and of course, raise any question. There should be a 10 minutes at the end of the presentation for that. So let's start. So to explain EnSilica, it's a company of around 170 now people. 80% are engineers, most of them silicon designers with various degrees of experience. Founded in 2001, so it's 22 years. Mostly based in Oxford at that time. Now is actually being spread over 3 continents. So we got sites in Oxford, 1 in Bristol, and 1 in Sheffield, and we've got a site in Brazil and 1 in India. The expertise is quite wide. Our business model is what is called a turnkey ASIC development. It can have various degree of complexity, but it can go more often than not into the situation where a customer with just concepts, sometimes even 20 slides explaining what they want, they come to us and ask us to build a silicon chip over those concepts. So as you can imagine, that means everything. It means architectural design of that chip, the partitioning between what should go into hardware, what on software. It means the design of IPs, and it means the implementation, and of course the DFT and so on. And the company also provides the logistics support for providing ASICs after manufacturing. So we don't have a fab, we are fabless, but we can help the customer to basically bring a single point of contact, like we are the gateway onto the manufacturing. So the customer will order parts from us and will take care of after development, engage with the fab, the packaging house, to then provide whatever number of ASIC they need. In terms of what we do is in various sectors. So the company is not just digital. So I'm the VP of the associate engineering, and the responsibility I have is in particular about digital designs. But the company has an analog team as well. And the combination of analog RF expertise, mixed signal and digital allows us to basically cover many applications. So as you can see here, automotive, we've got certification in the safety standard, industrial, RF, satellite comms, and healthcare as well. So diving a little bit into the technical topics, so I'll move now into more how things are done. So what you see here is the end-to-end, so let me close this. the end-to-end turnkey capabilities. So it's a bit confusing as a slide, but it's trying to explain what it takes to create a chip and what the company provides. So it goes from the top to the bottom. System level architecture is the first stage. And then there is like on the left-hand side, you will see the digital path and the analog path on the right-hand side, combining into physical verification and type out, the last orange bit. And then after that, we move out of what is called the development cycle, and we go into post-manufacturing, which is packaging, testing, and then all the rest, which is more complex than somebody may think it is. So chip supply chain management, the board level, the embedded software that goes with it, and the silicon validation. Of course, those chips will have to be validated before they can go into mass production, and if required, qualification, and so on. So that's probably the end of the overview about EnSilica. I think I will dive a bit more into how chips are done, into what the main silicon design functions are, and then where DFT fits. So what you see here, I'm not going to explain every single box in detail, but I wanted to give you an overview of the overall process. Designing silicon chips is a complex business. When you have to design something in a low geometry of a good degree of complexity, it will take probably something like between 50 and 100 engineers when you combine everybody. When you combine the silicon, the software, the validation, the PCB, the package, and so on. So it is a complex project to manage. So there are several degrees of project management that you need. Project manager and program manager are on top. You need somebody that defines the concept, the architecture of your system. And of course, you need a strong validation at the end. And what you have in the middle here in the green box is basically the entire development. So everything starts from the concept. So you have the marketing people who will describe in a sort of a list of high-level requirements what they need, what they want. The system architecture people are the technical arm of, if you want, of the marketing guys. And together they work together a lot to then break down those requirements into much more detailed set of requirements. They will say what goes into silicon, what goes into a software. So you have an algorithm, you may decide that that algorithm needs an acceleration. So you have to define a coprocessor or whatever other silicon IP, or perhaps not, and you will map the algorithm into a software program. They also define the use cases. They may put some constraint onto what IPs you want to use, like the protocols. So you will need PCI Express 5 or DDR4, certain performance, and so on. So basically, what you see on the left-hand side is more about what the chip does rather than how. The system architecture people will sort of constrain the how a little bit, but then most of the how the things is going to be designed is done in the green box, which is really the silicon development phase. So everything starts from the SoC architecture. So you can see the functions there that describes basically how the overall SoC has to be designed and where it goes into the floor plan and what level of security architecture that you need, how the system is going to boot, what clocking architecture you want, and so on. Then the front-end design is the RTL design. It's basically coding of Verilog for your blocks or your SoC. Functional verification. This is silicon. Silicon is not forgiving for bugs. Software as well. The difference between the software and the silicon really is the cost associated with fixing a bug. It's of course of a completely different scale when you design silicon. The cost of a bug fix may imply a complete regeneration of your masks, which is millions of dollars. It can go up to almost 10 million when you go into 7 nanometer. So you must have a strong functional verification here. So that functional verification, the yellow box, is usually many people. It's probably the biggest in terms of size in the various boxes there. Then you move into what is called implementation. So the last 3 boxes is transforming your net list which is at sort of logical level, into something physical. So you go the logical synthesis or the physical aware synthesis, place and route, and then the final sign-off that will give you the guarantee that you are meeting all the KPI, the key performance indicator, timing, power, and whatever. So you may wonder, where is DFT here? DFT in the past was fitting in the production synthesis. So if we go back in time to 30 years ago, DFT didn't really have a place in the overall design cycle because it was sort of hidden in that production synthesis. You synthesize your design, and at a certain point you add the scan, and that's it. It's completely different now. Not now, it's many years now. It's more than, I would say 20 years. DFT now is basically occupying the entire flow. So you need to think about DFT from time zero, from the first day you design your SOC architecture. Bear in mind that DFT is important. So I'm trying to explain that. Probably those terms don't make much sense, or some of them, depending on how much you know about DFT. But perhaps at the end of the presentation, we can go back to this slide, and those that terminology you see at the bottom of the slide will make a bit more sense. So DFT is not just scan insertion; it's also scan insertion. We'll introduce the subject in a minute, but it's much more than that. And it's incredibly complicated, depending on of course, on the chip. And there are more than one way to see problems and to face challenges when you insert DFT due to the wide range of applications and that you have in silicon design. So moving into test and DFT. So probably this is all clear to you, but let me refresh and explain the reasons why we need DFT. So the fundamental reason is that semiconductor manufacturing is imperfect, and that is something we have to accept. So you can spend ages into designing a perfect piece of silicon. You have verified everything. You feel fully confident that chip works. But unfortunately, when it's then manufactured and you got the silicon back from fab, it doesn't work. Some of the parts don't work or don't fully work. That is because the manufacturing itself is not perfect. And there are defects introduced for reasons that I will explain in a minute, that you have to deal with. And the only solution is to bin those parts. So you need to identify the parts which have those defects. Of course, you have to reduce the amount of defects as much as you can, but there will be always something left. So the yield is never 100%. What you see there, the yield is also a function of the die area. So the bigger is the die area, the smaller can be the yield. And it can be quite significant. But it's not, it's easy to, it's intuitive because, the bigger your chip is, the more wafer space will occupy, and therefore the more chances for that defect to hit the chip to make it non-functional. So testing is needed. Testing is needed to screen out devices which have physical defects. It's needed for other reasons. The main reason is to keep customer happy. The worst you can do is to give a faulty part to the end customer. So you don't want, of course, to have a faulty part in a pacemaker. You don't want to have a faulty part in a chip that goes into a satellite because it's not replaceable. But you also don't want to have a faulty part in an audio amplifier and have a customer return, which is a logistical nightmare and is very expensive, and it can damage the reputation of the company. So it's very important to do that screen out. Now, you may think quite rightly, why don't we use functional validation to identify the faulty parts? In the end, if there is a defect in a chip, for example, a net is stuck to zero or is cut, is broken. If that net is there, it must have a functional role. So there must be a functionality, a functional exercise of the device, which will trigger that net and will then present a functional misbehavior at the end. And that is actually correct. So from a theoretical point of view, you can always exercise your devices. Sooner or later, you will find a problem and you will then bin that part. So in theory, yes. In practice, no, for a simple reason that is just too expensive. So if you think about an ASIC as a system, it is indeed possible, if you just exclude anything which is like redundant logic, it is possible to reach through functional stimuli every possible net or transistor in the design and making sure that the stimuli are done in such a way that that net is presented, that mistake is presented as an incorrect logic value in one of the outputs of that system. So that is possible. The problem, as I was saying, is cost. So the time and effort to do that is absolutely prohibited for various reasons. So you might think, okay, you just say that functional verification has to be very, very exhaustive because you want to have a bug-free design. Yeah, but very exhaustive. So in complex SoC, we need to introduce a concept which is called hierarchical verification. So we don't verify the whole SoC in one go. The SoC is made of a collection of blocks or subsystems, which are verified standalone, of IPs, which are verified again standalone by other companies. So you acquire a PCI Express, you don't design PCI Express yourself, you buy from another company that is specialized in those modules, and they verify those modules themselves. So if you really want to cover the entire logical network that you have in your SoC, you should combine all those regressions together and run it. It will probably take, well, a full day to do that. So even if it's possible, which is not, it will take a full day. But think about a mass production of hundreds of thousands of parts that you have to produce. Think about, we got billions of smartphones. Even one day is absolutely unacceptable when you then scale up in mass production. So it is not a viable option. So also, this is validation. So it's not like a bug that you have to detect, where you can explore just a simulation model and identify that bug. This is a defect that is introduced in manufacturing. So it will affect one part, but not another. So you have to check every single part. That's really, that together with the coverage that you would need in your functional verification test suite makes this proposal impossible. So the solution here is to increase the controllability and observability of your system. So you need a way to reach basically the every single net easily, quickly, and make sure that basically every possible defect is transported out and observable in a very short time. So we talk about defects. So just a second, what are those defects when they are introduced? This is an example. It's probably not exhaustive. So you got mass contamination. Of course, the fabs take all the possible care in avoiding that, but it's impossible to avoid it. Dust particles, aging effect, you got metal migration, the degradation that you have in the oxide, and the handling is another source. When you handle dyes and so on, the electrostatic discharge can also introduce defects. So from an electrical perspective, those effects become shorts, opens, transistors that may become stuck on, so permanently on or permanently open, or more resistive effects. Of course, the logical effects of all of that is that the logic of your AND gate or OR gate or whatever becomes stuck to some value. So it's not actually functioning correctly. So one example. Let's assume you have this net here from A to the transistor T4, which is just broken. You go to T4 that remains open forever. So that is the electrical effect of that physical defect. From a logical effect, what you have, if you look at, this is an OR gate, if you look at the truth table, of course, if A and B here are both 0, you will have Z to 1 anyway, because T1 and T2 will bring the value up. If you got 0 and 1, you got B, which is 1, and T3 will be closed, so the Z will go to 0. Same for 1, 1. you got B that in the T3 that brings the Z down. The problem that you have is when A and B is 1, 0, because in this case, you'll have T3, which is open. T4 should be closed, but it's open. And T2 and T1, they're both open. So basically, Z is floating. So that's the electrical effect. The logical value of Z is basically whatever it was before. So there will be capacitive effects here that will keep Z at the value it was before. So if I ask you now, what is the test sequence that you need to apply for detecting such a mistake? That's really what DFT is in the end. So trying to find a combination of inputs that will definitely tell you whether this defect is present or not. You need 2 steps. So you need to apply something like 0, 0. So Z will go up to 1. Then you apply 1, 0. Now Z should go down to 0. It won't if there is a stuck at 1. If there is a break in that and MOS gate. So this is one example. May make another one here. A fault is detectable and testable if there is a vector. That's a general statement. So a fault is detectable and testable if you can find a vector T that can excise that fault and produce a complementary logic value at the stack-up point. And if you can also propagate the faulty effect to a primary output. So again, another example, this is, as you can see, is a mux. So it's C is the selector and A, B are the 2 inputs and Z is the output. So you want to check that there is no stack at 1 on that net G. You want to be sure that is not the case. What do? The logical process is you go backward, basically. So you want to make sure that Z becomes sensitive to the value that you have in G. So H has to be 0, right? So 0 as an input to your gate means that whatever is in G goes to Z. To have H0, you may decide you want to, B is 0. B0 means H0. That's fine. So this input is fine. And to have now G1, you want to have, you may decide to have so you want to impose the opposite value in G. So you exercise A0. So G would be 0. If it's really 0, then you go Z at 0 and everything is fine. If you have a stack at 1, then even by forcing a 0, you still have 1, and the 1 will transfer to the Z. So basically, the test vector to find this kind of fault here is 0, 0, and don't care about the value of C. So that's the logic that you use to identify a stack at 1, and something similar can be done for stack at 0. So with this, you can think, okay, fine, it would be very much more complicated with a very complex combinatorial network, right? But in principle, it's possible, and you can develop a software program that allows you to find those patterns for you. And that's exactly how it works, actually. Mm-hmm. So it sounds like we have solved the problem. Not entirely, because what happens if you have something like this, where you don't have just a combinatorial logic, you have an RTL, basically. You have registers, combinatorial logic, registers, combinatorial logic. Now, the problem is that you don't have a nice access to that net here, because you've got flops you need to, you have to set first. So the solution is what is called scan chains. And that's probably something you may have heard. Basically, you regain controllability and observability of your system by switching your system into another mode, a scan mode. You shift in all the values. So all the registers in the spatial mode are put together in a long chain. You shift the long pattern. You set the inputs to your combinatorial logic the way you want. Then you move into the functional mode. Again, you give a clock cycle, you propagate those values, and you capture the output on the other flops, and you scan out. And basically, that's how you move yourself into the previous simpler situation where you only have one combinatorial logic and perfect accessibility of primary inputs and outputs. So that's the solution, really. That's part of the story. So this is what we call scan insertion. Leo will explain more about the other techniques, which are more sophisticated than this, but this is the bulk, and this is what has used to be done in the industry for many years. Situation has become more complicated now, and we'll cover the other issues in the next slide. Just one consideration about the yield and the test escapes. So as I said at the beginning, what really you want to do with DFT is to introduce testing structures, DFT structures, that allows you to minimize the number of test escapes. So test escapes is what you are not able to find faulty. So there is no perfect DFT. So you have a percentage of parts coming out of manufacturing which are faulty. You run your DFT and you can identify perhaps a very good percentage of those, but some will escape because it's impossible to have a 100% coverage. So what you want to do is to minimize as much as possible the number of test escapes, is called. So what you see here at the bottom right, if you have like no coverage at all, 0, you go a test escapes, which is basically matching your natural yield, if you want. So basically everything will be a test escape because you're not covering everything. And that's what happens when you increase your coverage. You will start capturing more faulty. You bin everything that is faulty. Of course, the higher the test coverage, the less test escapes. That's the whole trick. So you want to achieve the highest possible test coverage. That's where the complexity is. So you want to do very high test coverage, but at the same time, you don't want to use a lot of inputs in your device because you don't have an infinite number of primary inputs you can use to scan in your data or scan out them. At the same time, you want to do that very quickly because test time is absolutely important. So there is a combination of many different reasons why the overall problem is not as simple as you may have seen in the previous slides. There is a cost with testing. Of course, those maxes you have seen, maxes you have seen here, they will add area to your device. And we just say that the bigger is the area, I'm sorry about this. Okay, so there's a cheap area overhead. So that's when you add DFT, more area. And because of that, there will be a yield reduction because the bigger is the area of your chip. There is a cost to DFT, but the cost of not testing is much, much higher. So there's pretty much no SoC today that is taped out without a robust DFT. I think this is my last slide before Leo perhaps will dive a bit more into the technical aspects of DFT. I wanted to point you the attention to what it normally means product success. That might be different from, it really depends. I mean, a success, particularly in academic field, is when you have an idea and you can prove that idea is successful. Basically, your idea works and is solving a problem. You don't really need to think about the robustness of that idea. That is another problem. It's an engineering problem. So when you move into science and research, success is something different. In engineering, very often, product success is really the commercial success of your idea. So if you don't have a commercial success, then normally, whether you like it or not, then the product is not considered in the end really successful, even if it's solving a very, very important problem. There are many examples of this in the industry. So with that definition in mind, you may wonder, what is more important really? Is the functionality of your device or the DFT? So you may think, okay, functionality in the end is what really matters. So if you are designing an SoC, a silicon, it's because you want to solve a problem. So it has to work, it has to function. And then, of course, yes, the DFT is also important, but it's less important. But Let me make an example. So assume that in a large set of features, which is what complex SoC today have, you have a minor one that doesn't work. Of course, you have to tell the customer won't be happy, but after some discussion, they may decide, okay, we can deprecate that feature. We can remove it from the data sheet. We can change our software to avoid writing the register with that value. And basically that misbehavior will never be seen by the end customer. So we lose a feature, but in the end, that product is still a success. On DFT, instead, you have a poor DFT, so you're not reaching a good coverage. So you will deliver to the customer a lot of faulty parts unknowingly. So the result of that is that the customer will then create whatever final product that will go to the end customer, and a percentage of those end customers will go back to that customer and say, my final product doesn't work. He has a glitch, he has something. So that is the customer return, which is the logistical nightmare I mentioned before, and is extremely expensive, and that can really damage the reputation of the provider, can affect the business, and there are examples even of startups that have closed because of that. So my message here is for mass production, DFT is as important as functional design. It's neither less nor more. Both have to be done well. Okay, Leo, do you want to continue with a bit more diving into testing and DFT?
Yeah, just to connect to what Davide was saying. So think about a car where there is lots of electronics in that. So if there is a single chip that doesn't work correctly, that there was I don't know, engine, control engine and things like that. So the car has to be returned. And that, how much would be the cost for the manufacturer for that? So that's why test is important. So here we're trying to define what is test. Test, as Davide also mentioned, is the process to ensure that all the devices which are shipped are free from defect and meet all the electrical parameters defined in the data sheet. So all devices are tested during the production multiple times because there are multiple steps in the manufacturing process. All devices are tested on special and very expensive machines, which are called ATE. ATE stands for Automatic Test Equipment. It depends on the complexity of the SoC, but for complex SoC, the cost of the machine is very high. So usually companies don't used to buy it, but they rent it for let's say houses that do this as a job. And the cost of seconds of testing on this machine is very high. So that's why with this, I want to introduce how important is the test time, because sometimes the test time makes up even the 10% or 20% of the total cost of a device. Yeah, let's continue. Well, probably Davide already anticipated that what we are testing for, so very well with an electrical point of view of what is going to, but from microscopic point of view, let's say, what is happening during manufacturing, the defects that can come are actually metal bridges, silicon substrate defects, photolithographic defects in the process variation and oxide defect. That's only the main, but it depends on the technology of the production. There may be other adding up to that. So we need to act in terms of DFT design to try to target as much as possible this kind of defect that depends sometimes also, as I said, from the manufacturing process and the node process as well. So the electrical impact, as Davide showed, is transistor stacked or open, resistive shorts or open, and excessive quiescent current. The consequences, as he said, are catastrophic failure, so chip doesn't work at all, or it might be that also it works, but the aging of the product is very low. It might fail after a few days of functioning, or maybe performance, affecting performance of the device. As Davide explained, these are what, from electrical point of view, means the defect. So I will go quicker because he's already very well explained that. What is design for test? As I said, DFT stands, probably we didn't say that, stands for design for test or design for testability. And it's the process where the test features are added to the design, which makes the device easier to test, and eventually with as much as coverage as possible. It works by having a test methodology, as everything, and a set of design rules which needs to be followed in order to get the higher testability possible in the shortest time possible. So the DFT technique's purpose is actually to speed up the test program development. The test program is the let's say the set of tests that will be sent to the manufacturing to apply to every device, and that's its a DFT task, DFT engineer task. DFT techniques needs to reduce, as I said, also the expensive tested resource. So the test time, sometimes it can go over for non very complex device over to few seconds. That's it. So you have to test everything in a few seconds, because otherwise the economically it's not feasible, the project. DFT techniques so needs to maximize the test effectiveness, as I said, and minimize the test time. That's the major challenge, let's say, of the DFT. So for what I said, the choice of the right DFT techniques is vital for a product, and they're not always the same for every kind of device. Why is DFT necessary? Probably Davide already said everything about this, but as he also said, as devices become more complex, test is becoming increasingly a large part of the overall cost of the device. So, and also, you know, it's very important, the time to market. So that's why we need specific, let's say, procedure to first insert the DFT logic in the device, and second, to generate the test, because it doesn't have to be, you know, a bottleneck on the because for some kind of devices, the test, the time to market is really important. So if you miss even a few weeks or months, you will miss the production, or let's say the market. Think about, you know, a device that needs to go in a toy. So you want to hit the time of the year where the production can be made in times for, let's say, Christmas, or for whatever festivity that toys are gifted, or things like that. That's really important for the customer. So obviously, there is, as Davide also explained, there is a trade-off. You know, the silicon area, the performances, which for very high-speed devices may be sometimes a problem. So we need to find solutions to that, because you're adding extra, let's say, logic on the way. That may slow down the device a bit. That for that bit enough that to screw up the functionality of the device. So, and obviously the engineering resources needed, which are expensive, and the design style restrictions as well. So the role of a DFT engineer is to architect the DFT, to design and verify and validate what is inserting, and to achieve the target test coverage. Sometimes the customer comes with a very clear requirement on that. Sometimes in terms of a part per million, the PPM Davide was mentioning in his graph there, the customer say, okay, but I want to buy millions of parts, but I want maximum, I don't know, 100 ppm. ppm stands for part per million. So the test escape cannot go contractually over 100 parts per million. So if you go over that, you pay some penalties, you know, to the customer. So it's, again, it's very important to have a very high coverage so that your PPM keeps under control. So for this reason, we need to create a standard solution where also to cope with unusual designs and polish the design community, let's say, within the company, to ensure that the final release they do of the design is truly testable. And obviously, we need to provide the solutions and tools for to make the insertion and the verification and all this process as much as automatic as possible to reduce the cost, obviously. The DFT technique, as we said before, it's functional testing. So that's a traditional chip test techniques and require obviously knowledge of how the design works, and can also add, you know, test structures like test pins of test pads, buses, and something like that. Structural testing instead are brainless regarding to what the device does. And that's the advantage of it. So they're much more prone to be made automatic. So essentially, the main technique is of structural testing is to reconfigure the state element in to give observability and controllability to the internal nodes of the device. And another technique is to insert BIST. BIST stands for built-in self-test, which are test-only circuitry to perform on chip testing on special structures, usually memories, but not limited to memories, also to many analog parts, you know, the famous look-back tests. That works for both scan and functional. And then for some technology, not all the technologies, IDDQ testing, where we configure the chip in a particular state using the scan chains Davide was mentioning, and then make some current measurement, which should be only the quiescent current. But if it's above that threshold, the device is discarded because there is probably a defect in the device. The device function. One of the DFT techniques, probably the most old design technique, is the functional testing. Tested device is operated in this normal functional mode, so it's impossible, obviously, to write code that tests everything in the chip, as Davide mentioned. So it's because it's actually impossible to control and to observe all the internal nodes without doing anything else. So the effectiveness of the test is very low. So despite the effort that one can make, even not considering the test time, which is huge, obviously we can barely reach around 50% of single stackette coverage using this technique, which is absolutely not viable for a production. So one of the most used techniques, as you can see from 1960, so it's very old, is reconfiguring all the registers of the chip in so-called scannable flops by adding a multiplexer here, as you see here, and some connections, so that what this will increasingly, this is massively increasing the controllability of stability, because actually we can control the majority and observe the majority of the nodes of the design, given the nature of digital design. So what's happening is that the first step we do for this technique is to convert all the flops of the design in scannable flops. Okay, then these are stitched together to form n, let's say, shift registers driven from top-level pads. Okay, so these pads here are not. They don't need to be specific for test. They can be functional pads reconfigured in test mode. And to do so, obviously, we need a test mode controller, which we load through a JTAG. I don't know if you guys have knowledge of the JTAG standard. So it's an IEEE standard where we use 4 or 5 pads to configure the test modes of the device. One of these test modes may be the scan mode. So when we are in scan mode, let's say these pads here are which are functional pads. So they're already there for functional purposes. They're configured as scan pads and so on. So we're going to have all the flops put in a daisy chain when we are in this particular mode, so that we can load any value on them for controllability purpose and unload the value after the capturing to check, to observe internal nodes. There is a problem that obviously we don't have many pads available for this, but we may have millions of flops in a design. So the scan chains you see here, each one of these is called a scan chain, may be very long, sometimes even 100,000 flops. So you need 100,000 clock cycles to load and 100,000 of clock cycle to unload it, which in terms of test time, it may be incredible high. If you consider that you have a very high coverage, usually you need something around 5,000 to 10,000 of tests. So that means 10,000 of loads, 10,000 of unloads. So a technique to reduce this problem is to add what is called codec, compressor decompressor. There's it's put a decompressor on the top of the scan pads here and a compressor here, so that the real internal scan chains are not, I don't know, 5, but maybe 500 here, so that they can be much shorter. This is the main technique used today to try to compress, that's why it's called also compressor, the scan chain length. Obviously, you know, as I said, there's a cost for implementing scan, which is the flip-flop becomes a bit slower and larger, obviously, and need to be, the scan stitching needs to be also done at when the layout is done at the routing time. So it adds extra, it occupies extra area also for the routing. So the benefit is, as I said, the scan is a structured DFT methodology, which is very high making, so possibly to make it automatic and repeatable, despite the complexity of the design. As we said, you know, this technique of direct controllability and observability of most of the internal nodes, there are several vendors that provide ATPG tool. ATPG stands for Automatic Test Pattern Generator, that given the design with this kind of structures is able to understand how the design is done and to generate automatically the vector, let's say, to load in the scan chains in order to maximize the test, the toggling of the internal nodes in order to get what Davide was calling stacked faults. As I said, this kind of vector are much more efficient than functional tests, and they may reach very high coverage, even around 99% of the possible faults, single stacked faults. And there is also a very high degree of diagnosticability, because if something doesn't work, the tool itself is able to load the data coming from the manufacturing and understand where the fault was. Because obviously you can trace back and see, okay, that's the flip-flop that is capturing the fault. What is the logic connected to that flop? And you have, by setting n different tests, you can realize, okay, the exact node that is actually stuck at what value. So that's really important also to give feedback to the production process, manufacturing process. So as I said, the technique is really easy. So we're loading the scan chain. The scan enable is the selector of the flop we were adding on the in front of the flops. So when ESI, obviously, we're not in functional mode. So we're getting the data from the shift, the scan, the chain, actually, the long, let's say, shift register. So we're loading it, and this loading is automatically calculated by the tool in order to increase the coverage, the toggling of everything. Then here, we put it back in sort of pseudo functional mode by putting back the scan enable. So the data now we capture here is actually the data coming from the functionality of the design. So this is the real test. This is just to set up and to try to sensitize as much as possible the chip. So this is where we actually capture the nodes of the design in the flop, and then we downloaded it. So the tool knows what to expect on each one of the flops here that we download after this step. So it's really easy to understand what's going on if something goes wrong. So yeah, I think we already, so it's, well, as I said, it's possible to have just a single scan chain that goes all over the flops of the device, but obviously the load time would be enormous, because particularly for big chips like with millions of flops, it would take forever. Probably the cost of the testing would be higher than the cost of the manufacturing itself. So a better solution, as I said, it's roughly to have all the scan chains of the same length, so that you share all the flops on as many scan chains as you can afford for pads you have for that device. And then another technique is the one I showed you before, is to insert the compressor that is shorten the scan chains with a cost of extra logic, obviously, but it's not much. IDDQ technique is very similar. The scan chains are still loaded. We still are in scan mode here to set up a sort of a quiescent state of the device. And then we make some current measurement where we have in mind already what is the acceptable quiescent current when the device is in a steady state. If it's higher than that, the part is automatically discarded. Obviously, this technique is has been sort of abandoned for some times because of the technology. When the nodes become the technology nodes became shorter, smaller, sorry, because the quiescent current was almost the same. You know, it was difficult to establish what was the right threshold to decide whether the chip was faulty or not. But now it's coming back because of the FinFET technology, which has again a lower quiescent current. Other techniques typically are, as I said, for the built-in self-tests. These are typically used for memory or for analog parts. And the test is actually all built in the design. What we need to do through the JTAG, so the test mode controller I showed you before, is just to set up the test, set up eventually the PLLs because we want to run everything at speed, and kick it off. The test automatically sends data to the memory, let's say, stimulating all the possible locations of the memory, and then through usually through a CRC, checking the results, it's the expected one. If it's not, the part is discarded. This test is really important for memories because memory are very sensible to manufacturing defect because they are much more dense than the digital logic. So the majority of the manufacturing defects are actually in the memories. And we need to have a very high coverage. Typically, the memory beast provided by the vendors, which uses several algorithms, guarantee a very high coverage, close to 200% of the internal memory cells. What is, as I said, because the memories are very sensible, and nowadays, you know, in an SoC, sometimes even 50% of the chip is memory. It's really important to find extra way to try to increase the yield of the chip, because otherwise, if it's most all of memory, you will discard good part. Despite having a very good DFT or coverage of your chip, you will end up to discard most of the parts. So what we do, we add extra so-called redundant rows or columns to the RAMs, so that when we test it, automatically recognize the built-in self-test, automatically recognize whether that memory is repairable or not, and write a sort of eFuse, which is on the memory, on the chip, to when that address is selected, automatically it goes to the redundant line rather than. So in this way, the yield of the chip increases a lot. Obviously, there are some, depends on the manufacturing fab, they have some requirements on that. So they said, according to the process we have, if you go over a sort of number of megabit in your chip, you need to have, I don't know, either 1 or 2 row or columns per memory if you want to keep the yield around 75% or whatever it is. So yeah, the built-in self-test, what it does for the memory is, but there are some for other parts of analog parts, which goes all over the memory with the data background and address and capture the response. As I said, the disadvantage of this is silicon area, because you're actually putting on chip something that it's only for testing, that has no functionality whatsoever for the chip itself. So yeah, as I was saying before here, so if you see here, for a mature process, if you, the yield can be very quite low if you increase the amount of megabit of RAMs. So instead, if we add some redundancy, or even called memory repair, then the yield goes up a lot. So as I said before, so what we usually do at one or more, it depends on how big is the RAM, one or more row or column, sometimes columns, for redundancy. And there is a register here that it's holding what it's reverting to the redundant line when one of the location is broken. So in productions, what kind of tests we do? We do a test on wafer. So before to cut the device and package them, then the packaging, and after the packaging, obviously, because this step may usually does introduce other eventual faults, so it needs to be retested. As I said, these are the machines we typically use for testing for big SoC, and they're called automatic test equipment. These are used for kind of test on the wafer, which are called EWS, electrical wafer sort. And the faulty parts are actually signed with automatically by the machine with a color, so that they don't get cut, they don't get packaged. We do EWS just to avoid, because the package obviously has its own cost, to avoid to package parts that are not working.
This is just for structural defects you are looking in this scan.
Yes, it's a scan and memory test. It's also structural. Yes, that's correct. It's not checking the functionality of the memory. It's just loading using some algorithms which are very well known, like 17N or 14N, to increase, the fault discovery. Several kind of fault type, not just stackette for the memory, also in the proximity and things like that. And the final test, again, we usually repeat the same test, but adding extra test as well, like AC parametric or DC parametric. Then, as I said, only the passing part to the EWS are packaged and then retested. And obviously, parts that fail are discarded, usually not binned, because they are later analyzed, all of them, to see if there is a sort of pattern to give a feedback to the fab. Then obviously this is a different kind of, all the tests we saw here, these are done on every single device before to leave the fab. But there are some other kind of tests that are done on the sample, some sample of the device, just to, let's say, evaluate the reliability of the chip, and also the life test. So what is called on OLT or burn-in. So usually what is done, we try to accelerate the life cycle of the device by putting it literally in an oven with very high temperature and stimulating it with all the possible tests. Usually the most toggling tests are the scan tests, what we mentioned before, and the memory bit tests. These are all run one after another for hours or for days. And then after that, sometimes we don't even check the results of all the tests, because the machine is not very accurate like the ATE. So it does, sometimes it doesn't allow to check that the test is passing or failing. So this is just to simulate really the device. Then the devices are retested on the AT and see which one are actually still passing and which one are failing. And there are some algorithms actually to establish, you know, if one is failing after a certain number of hours, what is the life of that in real life, let's say, of that device. So conclusion, manufacture is, as I said, as Davide explained very well, it's a complex and error-prone process, and test is about screening manufacturing defects, no more than the test as we intended as DFT. So design for test is about making fault detection easy and cost-effective. When this happens, so DFT, as we said, is a complex activity, and it needs to be considered immediately in the architecture stage of the design. So because we need to understand how the design is done, what needs to be tested, what needs particular attention. So obviously we didn't mention everything here, but there are lots of other sectors covered by DFT, like, you know, delay testing and because obviously in these nodes, let's say 7 nanometer, 5 nanometer, 12 nanometers, what is very important is not even the single stackette we talked about, but also to guarantee that every part that needs to be at a certain speed, let's say 1 gigahertz, really works at 1 gigahertz. And these are all a different sector, which we cover as well in the DFT activities. So as I said, DFT is much more than scan insertion. There are also timing constraints to be considered and everything. So why we do that, I think that should be clear by now. So without robust DFT, cost would be prohibitive for a device, and it won't be economical for the company. And as I said, mass production won't be possible, and as a result, there will be no silicon industry at all without DFT. That's all. You going with this?
You know as much as I do, but yeah, or even more actually. Yeah, no, the last point is an interesting one. Perhaps it's a bit overstated. So there will be no silicon industry without DFT. What we meant here really is, if you think about the cost associated with just constructing just one chip. Let's assume you just want to design one chip, no millions, just one chip, and think about the overall chain. Involving creating the fab, which costs billions, designing, educating people, and so on. So how can you explain that normally the cost of a device is actually like between $10 and $60, which is very cheap for something that contains a huge amount of intellectual effort. So when you build a bridge, that will cost many hundreds of millions, but a silicon chip, it costs only $10, $50. Well, it's not because it's much easier to build a chip than to build a bridge. The difference is that we build millions of chips. It's mass production that can lower the costs. But there would not be mass production without an effective DFT insertion. That's really the story. So that's the meaning of no DFT, really. There would be no mass production, and therefore no silicon industry, because we could never afford the cost of the old silicon.
So at the end, you know, if you have a wafer, it depends on the size of the chip, where you can fit a certain number of devices. If you have, so you can do this calculation ahead of the project, obviously. If you know the cost of the wafer for that particular technology, and the smaller is the node technology, the higher is the cost. You know that if you don't reach a certain yield on that wafer, so you actually no point to do the project at all.
Yeah, absolutely. Okay, we're not far from the end, actually. I would like to cover the non-technical topic about career and so on that I mentioned. So we got one small but real example here. It is small. We are talking about 28 nanometer. If I remember well, the size was around 20 square millimeters, so it's small, relatively speaking, but still complex enough to require a lot of sophisticated DFT techniques. Not all of them. There is much more that you will need in other devices. But here you can see the full scan design with the compression that was absolutely needed. The compression are localized where you see here. You have to pay attention to where they are actually, because they have to. Of course, the layout and the day placement has to be done with care. Otherwise, you will end up in infinitely long scan chains. So if you have that compressor spread or positioned in the wrong place with the scan chains on the opposite place, you can imagine the connections you will have on the layout and the impact that will have on performance, routing congestions, and so on. So you need to design how many compressors you want, where you want to put them, with floor plan awareness. So you really have to work together when you specify your DFT with your SoC architect who knows the functional subsystems, and with your layout lead or physical designer, design lead, who is now placing the blocks into your floor plan and decide the location of the compressors, but not only the location. The memory have to be bisted. Of course, you cannot have a memory bist per memory. You group memories together, and you have a memory bist for a group of memory. You need to pay attention now that you are grouping memories cleverly. Otherwise, you'll end up in the usual situation, in the situation I mentioned before, where you have long connections and you will never meet timing. So again, you need to be aware of where the memories are, what function they perform, what clock they have, and where they are going to be in the layout, and perhaps even give suggestions to your SoC architect to group or place those memories differently.
Yeah, what probably I didn't say is that all this stuff needs to work at the same speed of the functional device, because obviously you may want to test a memory at the same speed of the real speed that the memory needs to work in the application. So that's why what he's saying is really important. So the memory bit needs to be as close as possible to the memory that needs to be tested, because it needs to send the data at speed.
Yeah, so there is at speed path delay test as well on this chip. So the scan capture we mentioned before, yes, that can be done at low speed, and you can capture a very good amount of stack 0, stack 1 fault, but not all of them, because some of the defects are resistive. So they're not really shorts, they might be capacitive as well, which means they may not manifest themselves as low speed. But if you go in high speed, then there is a point over a certain frequency where the logic 0 will not be reached, and you will see a stack of 1. But if you go very slow, you won't see it. So that is a different class of defects called delay faults, which will have to be tested as well. So the DFT you have to insert has to be running at speed, and you need special structures for that as well, which is the on-chip clocking things, which again has to be, what speed of course, the speed you want to test them is the functional speed. There is no point to go higher than the functional speed, but you need, of course, to insert those extra DFT structures with an understanding of your clocking methodology. So again, as you can see, it's what I was saying at the beginning. You need to be really aware of your SoC architecture. You need to influence your floor plan. You need to activate your DFT as soon as possible. Otherwise, it will be too late. And that is something that, honestly, we have seen in the past. Basically the attention paid to DFT is not in sync with the need of the project. It's inserted late, and then you see a bit of a disaster at the end, where you don't reach the coverage that you need. Then you have to face a very difficult decision, because you made your calculation again and you discover that it's not worth to go to tape out and spend, I don't know, 3 million of masks or something that is not going to have a good number of test escapes. Okay, there's much more than that. So we haven't talked like boundary scan, which is another technique. Memory repair has been mentioned. The PLLs have to be fully programmable, because if you want to do all at-speed testing, you need to activate the PLL to achieve those high frequencies. So that means other logic. So that's what has been achieved actually on that design. So very good single stack cut, 99%. You did that, right? Yeah, that was you. Yeah. Memory test coverage 100%. Yeah, it's very good numbers. So this is absolutely ready for mass production. Okay, might be wrong, but this might be the last one, and perhaps we can go a bit slower if you can resist for another 10 minutes. So you may wonder, what are the skills for a DFT engineer? So of course, it's always difficult to identify skills of whatever profession here. From my experience, I think it has to be somebody methodical. I don't know if it was clear from this presentation, the difficulties that you have in this, but the variability of chips is so high that you can have many different situations that you have to understand and debug. So you have to have very good problem solving ability, you have to be patient as well, passion for details, that kind of, which is probably in every engineer in the end, particularly, I will say, on a DFT engineer. The DFT engineer is involved in pretty much all those steps. So it is a specialized function. So that has to be clear. At the same time, it's not something that will be done in isolation, because you need to work together with everybody else in the team. So it's quite a teamwork type of profession, but highly specialized at the same time. Yeah, you may wonder, how do you get into very experienced DFT? I thought I would put together those two classifications based on what I've seen in the market today. Of course, 0 to 5 years for a DFT engineer, that's completely, it's very difficult to be precise here. So I have seen guys very smart after 2 years that were senior already after 5 principal. Others that will never get into principal. You go all the possible variability, so don't read too much into those number of years. The senior principal is what sometimes is called DFT architect. So this is really the guy who says how DFT has to be done on an SoC of great complexity. It's a very high responsibility job. You get there after a good period of time. I'm making a difference between block level and SoC top level. So complex SoC are never done flat. Okay, so our EDA tools, I don't know if you have experience with Cadence or Synopsys or Siemens or others. There is a limit to how many number of instances they can play with. For big systems, you have to go into hierarchical design. So you have to partition. Think about this was one example of hierarchical design actually. So that cannot be laid out in one go. So you need to partition. If you can visualize some of the partitions here.
It's
and
5,
yeah, and then collate everything into a big SoC level. So when I say block here, I mean one of those partitions. So usually you develop your expertise there, under guidance by the SoC level responsible, who is typically a DFT architect, who think about the overall DFT architecture. The last point, yeah, the demand of DFT engineers clearly today outstrips the offer. There is I think everybody will tell you that, there is a significant chronic, hopefully not chronic, acute shortage of DFT experts in the worldwide job market. So it's not just UK, it's Europe, it's US, it's everywhere. So what we thought, and that's one of the reasons why we wanted to be here, is to pass you this message. It's very difficult. I totally appreciate it's difficult to introduce a DFT subject in a university lecture. It's very highly specialized and there is so much else to cover. Perhaps with this technical talk, we succeeded to bring you awareness of what DFT is. So at least you know what it is now.
So
you may wanna, yeah, and you may want to think about a career in DFT in the future. I can tell you that, yes, there is definitely a need. There's plenty of open positions out there in pretty much every country. So if you if you like the idea of specializing yourself into silicon design first, and perhaps in DFT or understanding more, of course, you can always make a change in career later, but that might be an opportunity. And I think that's probably it from me. Yeah, thank you for your attention here. I hope you're still still with us. And of course, if you have any questions, thank you.
Thank you very much. Thank you very much to our speakers. That was very informative talk.
Thank you for that.
I don't see any questions, people online. If you have any question, you can type it in the chat. Any questions here? Yes, Thierry.
Thank you for the education of DFT. I was just wondering, in terms of like long-termness of your job, in terms of like being in the business for like a long period of time, I was wondering, how do you see DFT engineers in the next like 10 years or 5 years?
Okay, I honestly will struggle to believe that there won't be a need for DFT expertise in the next 10 years. The main reason is that actually it's going the other way around. And the reason is that we are going down in technology. We are reaching, we are already with 5 nanometer, 3 nanometer, and the lower you go, the higher the chances of introducing defects in your chip. The yield goes down, and the more problems and the more aggressive you have to be in your testing methodology. So it's the other way around, actually. I think in 10 years, there will definitely be even more appetite for DFT expertise. I cannot tell you in 50 years, maybe there won't be any silicon in 50 years, we will change material, if we discover something. But definitely, from what I can see, there is no.
Definitely what I can tell you, and every time we change node technology, the challenges are even more and more and more in terms of DFT.
Yeah.
So as he said before, in the last probably 20, 30 years ago, that was the DFT position. There was still the DFT, but it wasn't as important as it is today. Today, there is no shift from the smallest to the biggest that has no DFT in it.
Absolutely.
So any semiconductor companies, they have DFT engineer in-house.
Yes.
I mean, this is not only a specific, so it's not like a semiconductor company said that, no, we don't need DFT. By functional testing, it's okay.
It's impossible. Okay, there is a difference. Perhaps it's worth to touch that point. The typical situation is you want to open a startup, for example. And of course, investing in silicon design is an expensive business. Okay, so it does take a lot of time to build a chip, and then it costs a lot to manufacture a chip. As I was saying before, is millions basically for a full mask set. So when you have an idea and you want to make it real, the first thing the startups do is to just rely on FPGA, basically. FPGA can be very expensive as a single part, but the process of creating it is not that expensive. And of course, you don't need DFT because you can always fix the FPGA.
Yeah.
Then typically what happens, if the idea is successful, there is a point in the life of a startup where they have to make a real silicon.
Yeah.
And it's a business reason, because typically you will sell the FPGA for hundreds of dollars or even thousands of dollars, and you cannot go into any mass production with that. It's only to prove that you have a good idea. So that's one reason. The second reason is performance. There is a limit of what you can achieve in FPGA performance. So there is a point in your life where you decide, okay, let's move to silicon. And at that point, you must consider DFT because, absolutely, yes. Every company has a DFT function.
Big company have a very large teams of DFT. Only as a R&D, let's say, a large team of R&D that makes all the stuff I was talking about, and then there is a group of DFT for each project team. So they deliver as a R&D the techniques and the tools to do that, and they apply to the specific chip and so on.
Yeah.
So yeah, there is a big demand because of that, because particularly in the last 20 years, it's exploded.
Yeah. And you have mentioned that they should start working even from layout design engineer, process fabrication. They should work together, because
Absolutely.
all of these test components that you mentioned, they should start developing the design along with the other components in the chip. So it means that if anyone has interest in layout design or process fabrication, I mean, they could still have this interaction with other engineers and learn from them in other.
They need to have a minimum aware of DFT, even if they don't do that. In fact, we have a specific, let's say, course that we sometimes deliver to the design community of the company, just to make them aware of what DFT is and why we sometimes ask for that rather than this.
Yeah, there has to be some DFT awareness in every, let's say, collateral function. So an RTL designer should be aware of DFT issues. It doesn't need to be a DFT expert, but at least he has to know the consequences of writing the RTL in this way or the other way. It's not always easy, I must say, because yeah, naturally you think about functionality. You don't care at the beginning about DFT considerations. So there has to be an effort from the DFT experts to continuously remind the front-end designers, the RTL designers, about the consequences of, I don't know, writing a clock gating structure in a way rather than in another way. And so, but yes, definitely that's that awareness.
Any other question?
Is the PowerPoint available on Blackboard?
If this is available, the slides? Sorry. Yes, I think it's fine. Yeah.
Upload the video recording in our website. Now, actually, the student branch website later, you can rewatch.
Yeah. Sure. Why did I decide to join the company? Oh, that would deserve probably like half an hour. Okay. There is something peculiar about EnSilica, and I actually joined the company, just to be totally open. I joined the company in July last year, and the company where I spend most of my time, and the same for Leo, is ST Microelectronics, which is it's a giant in silicon industry with 50,000 people across the world, much bigger than EnSilica. Now, the peculiarity of EnSilica is, well, two things. The first thing is a small company where every function is easily accessible. So if you want to talk to a marketing guy, because you want to know more about why we are doing that chip rather than the other one, it's there. It's just around the corner, you talk to that guy. Everybody, and the same for architects. And so it's that size of the company, let's say below the 500 people, which is a nice place to work with. We are growing, so perhaps at some point we go over that limit where we need to organize ourselves like a very large company and so. But so far, it's a nice place to work with. The other one is we offer many different kind of applications. So we do have our line of products which are EnSilica silicon, but the core business in the end is create silicon solutions for others. So that means there is an incredible variability of solutions. So the kind of problems we face are very different for every chip. So we go for very small chips that do audio processing, for example, which is tiny in robust, let's say, old technology, but perhaps very, very low power, like microwatts sometimes. So you got challenges on that side. Maybe part of it is analog, and so on, into very large, like 5G communication devices, hundreds of square millimeter, where you need a lot of the solutions we discussed today, and much more for DFT, and not to mention all the rest with architecture and physical design. So that's the nice thing. And as a consequence of that is, yes, you face new challenges every time. What happens in large industry is that because they specialize, if you are a company that is doing specialized in a line of product, the result is that you can automate a lot of your design flow. Because you're facing similar problems because you're doing a set of boxes, and you do a family of set of boxes, then the next family will be similar but higher resolution. You go 4K, 8K,
Similar.
but it's similar. So the level of automation you can introduce is a lot, and the result of that is
Push button.
well, there are always problems to solve. It becomes a bit more repetitive. Of course, there are always a lot of intellectual challenges to solve. Don't get me wrong. On a company like EnSilica, because we don't do, we are not specializing into a single line of product, but we are open to the customer basis, then we can go from a huge variety, and we are introducing automation, but it's of a different kind. And I can tell you a couple of years in a company like EnSilica will make you grow a lot. Then you will be able to face many challenges because of the nature of the business, not because we are more clever than others. It's really the way we operate that will force you to understand and to apply that continuous intellectual effort every time. I hope I answered your question.
And can you explain in Bristol office which part you are focusing on?
It's mostly digital. There's one guy actually who is analog, but the rest is digital. So we go. Let me see if I can go back to. Let me go back here so I will be more clear. Yeah. So basically we have the SOC architecture bit and the front-end design, the functional verification. We go all of it actually. Yes. Yeah, because so everything which is digital. What we are missing, we got DFT. We need to become stronger in DFT. We need these as well. Yeah, it's to be honest, it's not just Bristol. We need these in, we got many projects to do. And as I said at the beginning, managing those kind of projects require strong and solid project managers. So that's we do have a PMO office, of course, but yeah, we are hiring in those two, and also in functional verification. And so we are expanding, as we probably discussed last time. We are trying to expand at the right rate. I have experience in other companies of too rapid expansion and not being able to follow the new joiners the way they deserve to be followed. So it has to be done at the right pace. So we need to find the right people, incorporate them, make them active, follow them, supervise so they can grow and they can contribute to the company as possible. Yeah, but to answer your question, yes, it's pretty much the whole thing. Yeah. In terms of having the key skills, then of course we are not a large team. It's, as I said, 16 people. So we got very senior, not to say old people, but with a lot of 20 years of experience, all of us. We need to bring fresh and young and fresh people. That's really what I like to do.
Yeah, this is very great. I mean, you have an office here, and it is very important for graduates
of course.
Of our university. I mean, they can take advantage of the presence of your company in this city. So, and they will have more room to explore new ideas.
Absolutely.
When the company is not in, I don't know, you mentioned below 500.
Yeah.
But it is growing, but it means that you will have more room to explore new ideas, absolutely, new solutions. So this is very important. Yeah. Any other question? No? And I don't see any question online. Let's thank our speakers again. Thank you very much.
Thank you, guys.
And for people online, so I hope to see you in our next event. See you.